This video will discuss ANOVA analysis. We're going to discuss three types of ANOVA analysis: single factor, two-factor ANOVA using a randomized block design, and then a complete two-factor ANOVA. The first one, the single factor ANOVA, is done when you already have data and you just want to know if there's a difference in the samples based on different treatments. So this is like data that's already been collected. You don't have any choice in how you set up the test. You just want to go through and run this. So examples of this, you would have data on car crashes and vehicle types, and you want to see if insurance claims may vary across vehicle type, something like that. But for the single factor, it's not really an experiment that you've set up. It's usually just something that you've gathered the data for, and you're just examining it. The ANOVA with randomized block design is otherwise known as a two-factor without replication. This is done when you want to study the impact of a treatment, but you recognize that another input may influence your results. So an example of that would be analyzing new sales strategies, comparing end-of-month sales by employees using the different strategies. So recognizing that different employees may be better salespeople, and therefore that may have an impact on your sales that you're having. And then the two-factor with replication is done when you want to examine the impact of two or more treatments or effects. An example of that, so we're going to look at a printer company who wants to know whether or not they should use television, radio, or newspaper ads in order to sell their printers, and whether or not the type of ad used depends on the price that they charge for the printer, that kind of thing. So, when you're considering two or more treatments or impacts that may have an effect on your data. So we'll start with the single factor ANOVA. The model without treatment effects is denoted as such, where Yij is the jth observation for population I, and mu I is the mean of population I. So that's the model without treatment effects. So you've done nothing to have an impact. And then with treatment, you have that mean plus the changes in the mean based on the factor or treatment, which is going to be denoted with your little gamma I there. So assumptions that are involved in here: the errors have a mean of 0. They have a constant variance, and they are normally distributed. So the same type of assumptions that we had involved in our regressions that we looked at in chapter 6, I believe. And that's because ANOVA is, a critical part of running our regressions. And this type of analysis is equivalent to a regression where the dependent variable y is a dummy variable. 1, it has an impact, and 0, it does not have an impact. Okay, so that's why you saw me relating that back to our interaction or dummy variables when we were discussing that in chapter 7. So again, just repeating that again, this type of analysis is equivalent to a regression where the dependent variable is a dummy variable. It takes the value of 1 when the treatment does have an impact, and 0 when the treatment does not have an impact. So we want to ask ourselves, are all population means equal? Which is the same as asking, are all treatment effects equal? So HO, all of the means are equal, or all of the gammas are equal. HA, at least one of them is different. And both of these can be found using an F test. So we're just going to look at the p-value of the F statistic on our Excel or SPSS printouts. The higher the F statistics, the more the difference in the means can be attributed to the treatments or the factors being examined, and thus the less likely it is that HO is true and therefore should not be rejected. So we start off with this, so here are the steps in steps in SPSS. It requires you to rearrange your data into 2 different columns. So be careful about that. There are going to be a couple rearranging type things that are going to be involved here in SPSS that you won't necessarily need to do in Excel. And here are your steps in Excel. You can see the examples to go through and look at that. The first example uses injury data. So it compares the number of injuries for 9 different car class types. And we want to know whether or not the number of injuries differs based on car class types. So here is our SPSS printout. We're going to look at the significance of that F statistic. That's roughly equal to 0, so it's definitely less than 0.05. Reject HO. The average number of injuries does differ by car type is what we find there. And here's our output in Excel. And again, we're going to look at that p-value. Again, it's roughly equal to 0. So HO was the average injuries are equal across the 9 classes. We're going to reject HO and find that the average level of injuries is different across the 9 car classes, or does depend on the car class type. Now, there are 2 methods that I can use to further examine this. This Bonferroni method can be used to compare multiple treatments, not just pairs of treatments. It's done when we want to compare more than 2 different impacts, more than 2 different treatments. And I have this information here. SE is the square root of the MSE within groups, and then B is a t-value for alpha over 2 times the number of comparisons. The number of comparisons you'll see in the example video is denoted as G, so this is the t-value for 2 times alpha, alpha divided by 2 times G, based on the degrees of freedom between groups is what we're going to use in there. If 0 falls within this range, then it tells us that the approach or factors or treatments are not different. In other words, there is no, approach A is not better than approach B, or treatment A is not better than treatment B, something like that. The Turkey approach follows the same basic methodology. It's going to be used to test the same things, approach I versus approach J in this case, and it's used to examine all pairwise comparisons of treatment means, not just looking at 1 or 2 of them individually. Now, I do show you how to do this both in Excel and in SPSS, but I will be honest, it is a lot easier in SPSS. You literally just check off Turkey and Bonferroni, and it spits out that data for you. And you can see that just by looking at the length of the videos for each of those examples. Okay, so the data set used here is Comp Sales 9. It contains information about 3 different sales approaches for 15 different salespeople, and each salesperson, each sales approach was assigned to 5 salespeople. And the end of the month, they collected sales figures to figure out, which sales approach was better. And you want to test, start off by testing, are all 3 approaches, equal? Is there any statistical significant difference between them? So you run your
So to get this output, I follow the same process as I did before. Select data, then data analysis, ANOVA for a single factor. I input all of.
But then you want to know, and you can confirm the same thing using SPSS, but then we want to know which approach is better. So we can look at the Bonferroni method. Here's the output from Excel. G is the number of comparisons, so we're going to be doing 3 comparisons, approach A minus approach B minus approach C, and approach A minus approach C, or you can just say there's 3 sales approaches, so G is 3. 2 times alpha over G is going to give you this probability, and you're looking up this B is this t statistic for this given probability that you're going to be calculating there. And you follow the formula. Let's see, formula as shown right there. So the average of A minus the average of B, and then this upper bound is using this plus, this lower bound is using this minus, and we go through here, and anytime 0 is within the range, it tells us there is no statistical significant difference between the two approaches. So we see there is no statistically significant difference between approach A and B, or between approach B and C, because 0 is within that range, but there is a statistically significant difference between approach A and C, because 0 is not within that range. And this also actually tells us that approach C is better, because we're getting A minus C and having negative results. So if we flip this around and compared C minus A, we would get those same numbers as positives. The Turkey method uses the same, follows the same basic approach. The information can be found on your, the information for the Q statistic can be found in table, I believe it is B11, the studentized T distribution. You can find it in your book. And so we'll go over that a little bit more in class, how to find that value, but you're going to have a Q value that you're going to use constantly. And you're going to follow the same basic methodology. If 0 is within the bounds, they are not statistically significantly different. If 0 is not within the bounds, they are statistically significantly different. So again, here we're confirming that, there is a statistically significant difference between sales approach A and C. And I can see all of that in my SPSS output here. Using Turkey, this is approach 1 minus approach 2. So sales approach 1 was sales approach A, and 2 is B. So here, the upper and lower bounds, there's a 0 within there. So it's telling me there is no difference between 1 and 2, but there is a difference between 1 and 3. And here, notice this does 1 minus 3, so these numbers are negative. But down here, when I do 3 minus 1, I get the same numbers as I did here. Obviously switched my upper and lower bounds. And now those numbers are positive. And same thing for the Bonferroni down here. There's no difference between 1 and 2 because 0 is within that range. But there is a difference between 1 and 3. And so this is 1 minus 3. Down here is 3 minus 1. So this is telling me that using sales approach 3, which is sales approach C, I sell between 4,000 and 20,000, roughly 21,000 more using approach C or approach 3 than I do using approach A or approach 1. You can also see here there is no statistically significant difference between 2 and 3, and that's confirmed using both the Turkey and the Bonferroni method. The next thing we're going to look at is a randomized block design. Here we have 3 sources of variation: blocks, treatment, and error. So let's consider again our computer sales problem that we looked at before. There may be another factor that we didn't consider when we were examining the 3 different sales approaches. Maybe some people are just better salesmen regardless of the approach used. So if we were actually able to gather that data ourselves, we would probably, like to take into account whether or not that person is a good salesperson. In which case we would do this by grouping the data by salespeople, which is not something you see occurring in the previous example that we just did. But if you're going to design your own ANOVA analysis, you can go ahead and do that. So here we're looking at your impact is equal to your average plus gamma I is the effect of the ith treatment, and Bj is the effect of the jth block. So this method allows you to control for external factors by creating blocks. So if we were to go back to the previous example where we were looking at computer sales, you would say like gamma, that first treatment is the sales approach used, and then B blocks is like the salesperson. So the data gathered for the next example was gathered keeping that idea in mind, that there may be another factor that's influencing your results, and you should recognize that factor. So here we have serial 9 data. We have data on 4 cereal box designs from 20 stores, and the goal is to determine whether or not the box design leads to more sales. So, with the ultimate goal of trying to pick the best design. But they recognize that there's a problem that larger stores may sell more cereal irrespective of box design. People just go in there, more people go in there to buy cereal, and they don't care what the design looks like. So the solution was to group the stores into blocks based on size. So recognize the impact of that block, and then once that's taken into account, you can analyze the impact of the treatment. So our question is, do the box designs matter? In other words, do the treatments matter? So you're going to go ahead and run a 2-factor ANOVA without replication. So in Excel, it's data analysis, 2-factor without replication. And we want to know, is there a difference in the treatments? Now, based on the way we had the data set up, we'll look at that again here. The rows are the sizes, and the columns are the design. So when it goes down here, we do find a statistically significant difference based on rows. We do not find a statistically significant difference based on columns. So our rows were our blocks, our store sizes. So there is a statistically significant difference in cereal box sales for the different size stores, but there is not a statistically significant difference for the cereal sales based on the columns, which are the designs. Okay, and I'm just finding that looking at those p-values. So here are my steps that I would go through in SPSS. Notice it is a little bit more complicated to set this one up. You may just choose to run this in Excel as opposed to running it in SPSS. But it's going to give us that same output. So the blocks are not found to be statistically significant. The treatment is, and this actually has these 2 columns. The names were actually reversed. The treatment, it should read treatment as design and block as size. So I had this slightly set up wrong. So if we take that into account, and when we're looking at this, the block should be the size, the treatment should be the design. So if I'm looking at that here, I'm saying that design is not statistically significant, but treatment is but size is statistically significant. So the same finding as I had with Excel. Then I can run a 2-factor ANOVA. My 2-factor ANOVA is done when I want to examine the impact of 2 factors or explanatory variables. This type of problem is called factorial design. When all possible combinations of the 2 factors are used, it's a complete factorial design. So this is like looking at the impact of 2 different treatments. So my coefficient alpha is going to be the impact of factor A. My coefficient beta is going to be the impact of factor B. And then I'll have my interaction term between A and B. There are 3 hypotheses that can be tested using this model. The tests of the main effects of the treatments the tests of the effects of the treatments, A and B, based on the coefficients alpha and beta, are called main effects, which is what I'm actually interested in, but I need to check the significance of the interaction term first, because the effect of treatment A may depend on treatment B and vice versa. So only when I've ruled out that there is an interaction effect do I go on to test individual effects. So you'll see HO, all the interaction terms are equal to 0. Test that first, written in red. The impact or severity of the interaction, if any, can best be understood by looking at a means plot. So you plot the average value of y that occurs for each treatment. If the lines are roughly parallel, it is a signal that there is no interaction. So HO, look, HO is going to be there is no interaction, and HA is going to be that there is an interaction. Okay, so here are the steps in SPSS, roughly the same as you saw for the two-factor without replication, except you don't need to go through and go into that model area and make those additional changes. So here's the example we're going to do. It's using printer 9 data. A company wants to examine the impact of 2 treatments on printer sales. The 2 treatments are price and advertising type. They're looking at 2 prices, either 600 or 700, and 3 advertising types, TV, radio, or newspaper. So price 1 is 600, price 2 is 700. Then advertising 1 is TV, advertising 2 is radio, and advertising 3 is newspaper. And we plot our treatment effects here, and we do see an overlap, which means there is an interaction effect. So I will find an interaction effect, but you know, they don't really cross over until between treatments 2 and 3. So we're still going to go through and run through this entire analysis just for practice purposes. Okay, so run the two-factor ANOVA with replication. First thing, are there interaction effects? HO is there are no interaction effects. We're going to reject HO. We do find interaction effects. So interaction effects between the 2 treatments do exist. So we find that price is affected by advertising. So that would tell us I probably want to stop here. I'm not going to get so much statistical significance from the rest of it because there is this interaction, but we're going to keep going as an example here. So does sales price matter? I'm looking at that p-value. It's less than 0.05. So yeah, sales price does matter. Sales price is going to be that sample. That was the rows. And be really careful when you do this two-factor ANOVA with replication. It's going to ask you for the number of rows per sample. So that was recognizing that there were those 2 prices. And then columns is advertising type. Does advertising type matter? Yes, and we find that it matters even more so than the price does. So what should the company do? Well, we see that on average they sell more with price 2 than price 1, which is, I'm sorry, with price 1 than with price 2, which is not surprising because price 1 was less than price 2. More people like to buy things that are cheaper. And then, you know, when we look at advertising type, which one looks best? Well, type 1, which was TV, appears to be, you know, that has the highest averages. So type 1 is better. And then when I consider that interaction effect, price 1 is better with advertising 1, and price 2 is also better with advertising 1. So overall, I would say, based on this information, sell at 600 and advertise on TV would be my recommendation from this data. And here is that same output using SPSS, and we can see block times treatment. You do see that interaction effect that's coming into play there. I have the blocks listed as advertising and the treatments listed as price. You can call them treatment 1 and 2. You could have called them advertising and price. You could have done whatever you wanted. I just happened to stick with block and treatment. So I'm seeing that both blocks and treatments, in other words, both advertising and price, are statistically significant. And again, I do find that advertising type is more statistically significant than price is because it has a lower p-value.